you up to speed where we are. One more step. If I write these down. Oh, no, here you go. I think we had different ones here, if that works. Oh. Okay. So, what do we have? Right, oh, but yeah, back before the 4 plus 3i, so it's 1b minus 3a. That's what we call an S in this class. So we're diagonalizing matrices, and we've done the lecture long enough to explain why that's a good thing to do. And we know the process for diagonalizing matrices is subtract lambda off the main diagonal, compute the determinant the AB minus BC, set it equal to 0. We use the quadratic formula to get these two eigenvalues. We worked out how to get the corresponding eigenvectors. And then we can break this down into a D and an S like we had before. And if you work it out, if you calculate the inverse of S, which you know how to do for 2 by 2s, and do S times D times S inverse, that's going to get back to the A. And the whole idea of the factorization here is this was a diagonal matrix, and the eigenvectors gave us a basis. Let's back up. So essentially what I'm doing is instead of working with the standard basis, I make a better basis. And then if I write my input vector relative to that new basis, the transformation is represented by a diagonal matrix. So the diagonal matrix could cut up the fact that both x and y increase by 10%, both x and y decrease by 10%. And what's a little bit weird about this one is we started out with the matrix just with real numbers in it. And when we do the D and the S, we end up with imaginary numbers. So our goal in this section is to try to get this as a factorization. So essentially find a good basis. And we want this to be a nice matrix. So it's going to have some interesting structure. We want to make sure that we only use real numbers in the factorization. So if our problem starts out with just numbers, we want to be able to do any problem where we apply this matrix in just real numbers. And then I realize that you've never had a lecture explaining exactly what imaginary numbers do. So we talked about this last time. And this here is the real number line we've been using since first or second grade. And then the last thing I told you is there's an imaginary number line going perpendicular to this. And then it's Because one way to think about numbers is vectors along a number line. So I can think about the number 1 as this vector, and 2i as that vector. If I add these two together, the tip to tail is 1 plus 2i can be represented by either this point or this vector. 3 minus I would be down here, over 3 and down I. And what's interesting about complex numbers that we didn't have with vectors is we can multiply complex numbers together. So, the example I have here. Last example we had. If I'm going to do I times 2 plus 3i, 2 plus 3i is there, or in the vector form it's 2, 3. And remember we talked about multiplication by I rotates 90 degrees. The algebra here, that's 2i plus 3i squared. And remember that I squared is negative 1, so that's negative 3 plus 2i. So negative 3 plus 2i is there. Let's draw this. Colors. As a vector, that's negative 3, 2. Good. Do these really meet at a right angle? Is that really 90 degrees? And how do you know? How do you take two vectors and check to see if they're perpendicular or not? The dot product. Is the dot product 0?
Yeah.
And you can kind of see how this has to work. Just multiplying both sides by I is this part becomes the imaginary part, and this, the sign changes. And this is the secret. So multiplying by a complex number, by any complex number, is going to rotate by a certain amount and scale by a certain amount. So, let's look at 1 plus I. One plus I times 1, any number times 1 is itself. So what happens is I'll think about 1 as a vector, and then multiplying by 1 plus I brings me out here to 1 plus I, over 1, up 1. So what angle does this make? 45 degrees. Okay, and as this one starts out with a length of 1, is how long is 1 plus I? If I go over 1 and up 1, square root of 2. So I can think about multiplying by 1 plus I as rotating by 45 degrees and stretching by a factor of square root of 2. I'm going to clean up over here and break that down. if I do 1 plus I times 1 plus I, so times a 1 plus I rotates by 45 degrees. And if I do 1 plus I times 1 plus I, it's going to rotate by 45 degrees twice. Which is the same as multiplied by 90 degrees. And if I scale by square root of 2 twice, so it starts out length 1, then length square root of 2, and then length square root of 2 times that, what's that going to be a scale by? 2. So let's do it. If I start with 1, rotate it by 90 degrees, and scale it by